Good morning class, good morning to all. Welcome to Jatin's Academy. Today in this class we will learn about the second chapter of physics, class 10th ICSE, that is work, energy and power. So in this chapter we will learn about the definition and types of work. Next we have definition of energy and energy as a work done. Next topic we have various units of work and energy. After that we will do definition of power and its units. Next, different types of energy. Then potential energy and kinetic energy, which is a different types of energy with derivation. Derivation is very important here. Next we have types of potential and kinetic energy. Next we have conservation of one form of energy into another. Here we will do some examples. And last we have principle of conservation of energy. So these many topics we will do in this chapter. So let's get started. Let's start with the first topic. First topic we have work. So before understanding the definition of work, let's understand the examples. Means from the example we will see in which case work is done on a body and in which case work is not done on a body. So from the previous knowledge, just tell me in which case work is done and in which case work is not done. First example we have a person pushes a wall. As person is applying force on the wall, but in this case displacement of wall is 0, so work is not done here. Next example we have a man is walking on the ground. As man is walking on the ground, force is applied on the ground and the man is moving in the forward direction, so here work is done. Next example we have a man is studying. While studying, although it is a mental work, so mental work is there, but according to physics point of view, physical work is not there, so displacement is 0. So here work done is also 0. Next example we have while eating. While eating also, this is not considered under the work of physics, so here also work is 0. Next example we have while bicycling. Means when we apply the force on the bicycle and the bicycle moves in a forward direction, so in this case force is applied and displacement also occur. So this is the example of work done. So work is done here. Next example we have a person is applying a force on a body and body also move, but here work done is 0. This example is little bit complicated, that also we will do in further next part in special cases, but for the time being here just see a person here, the weight of this arrow is in the downward direction, which is a force, and the displacement occur in this direction. So although force and displacement is there, but angle between them is 90°, so that's why this work done is 0. But still this special case we will do in the next part. Next we have a boy is applying a force on this dumbbell. So here force is applied and displacement of body is also occur. So here work is done, but here work is not done. So now let's see the definition of work. So work is said to be done only when force is applied on a body makes the body move. It means that when we apply a force on a body and body displaces, so this is actually the work done according to the physics point of view. Means we are applying the force and the body moves in the direction of force, that is called work done. So now let's derive the formula of work done with some example. So one example we have two boys moving this roller. So as two boys moving a same roller, so they are applying the same force. So when they are applying the same force, so in this case force is same, means this is a boy, this is B boy. So force applied by A boy is equals to force applied by B boy. But the displacement of occurred by A boy, means displacement covered by A boy is more than displacement covered by B boy. Now tell me, out of A and B case, in which case this work done is more? So if you see carefully, here displacement is more. It means this boy apply more work done in order to move this ball. Although the force is same, but displacement is more in the first case, in A case. So that's why work done in A case is more than work done in B case. Now if you see the result, means if you conclude that what is a relationship between work done and displacement. So here work is directly proportional to displacement. Here S signifies displacement. Okay. Now carefully see, work done is directly proportional to displacement means more is the displacement, more is the work done. Now let's see one more example. In next example, both boy covers the same displacement. As both boy covers the same displacement but force is different. In first case, roller size is bigger, so this boy has to apply more force. So force occurred by A boy, force applied by A boy is greater than force applied by B boy. Displacement in these cases are same. So now tell me in which case work done is more. As this boy has to apply more force, so in this case, in A case, work done by boy is more. So work done by boy A is greater than work done by boy B. Now let's find the conclusion from this part. So more is the force, more is the work done. So work done and force are again directly proportional to each other. So now from these two formulas make the formula work done. Work done is directly proportional to displacement, work done is directly proportional to force. So from these two equations, work done is directly proportional to force into displacement. Directly proportional sign we will convert it into equal to sign by adding a constant k. Okay, so now take k value as 1. So now here we got work done as force into displacement. So what is work done? Work done according to the measurement point of view. Measurement means in order to find the value of work done is force product of force into displacement. So now let's see the definition of force work done. So definition of work done, we have the amount of work done by a force is equal to the product of force and displacement of point of application of force in the direction of force. What is the meaning of this? Carefully see, work done formula we have force into displacement of point of application of force in the direction of force. Here for example, I have one block and I am applying a force on the block. So this point where I am applying a force, this point is called point of application. Point of application of force. When I am applying a force on this block, so the block moves in this direction. So the block starts moving in the direction of force. As the block start moving in the direction of force, so that only is a work done. Means force is in this direction and displacement occur in this direction. So product of these two values gives a work done. So definition must now it's clear that work done, amount of work done is force and displacement occur in the direction of force. This part is very important. Okay, so now let's talk about that work is a scalar quantity. What is the meaning of this? It means that work does not depend upon the direction. What is a scalar quantity? Which only depend upon the magnitude but does not depend upon the direction. It means that if you apply force in this direction and displacement occur in this direction, so you will get some work done, F into S. Now apply the same force in this direction and same displacement occur in this direction, so again you will get work done as F into S. It means that although you are changing the direction, force and displacement value is same. By changing the direction, magnitude of work done will not change. So if magnitude value of work done or any sign will not change, positive negative sign will not change, so it means that work done does not depend upon the direction. When any quantity does not depend upon the direction, that quantity is called a scalar quantity. So that's why work done is a scalar quantity. Okay, now let's see the expression of work when force is applied not in the same direction of displacement. What is the meaning of this? Carefully see, In the previous definition, we have seen that work is done on a body when force is applied on a body and body displaces in the direction of force. But here the body not displaces in the direction of force. Why? Because force is acting in this direction and displacement occur in this direction. It means that force and displacement are not in the same direction. So what is the formula of work done when force and displacement not occur in a same direction? That formula we have to derive. Okay. Now let's see how we will calculate the work done when force and displacement is not in the same direction. So in this case, force is applying in this direction and displacement occur in this direction. So force direction is this, displacement direction is this. So now what we will do, carefully listen. We have two choices according to the definition of work done, that is force occur in the direction of displacement. So what we can do, either we can take displacement in the direction of force or we can take force in the direction of displacement. So in this expression of work done, what we will do, we will take displacement in the direction of force. So if you will see, here we have three directions. If I make a right angle triangle here we have three directions, named it as A, B, C. So here we have AB direction, BC direction and AC direction. AC is the actual displacement covered by the block, but AB is a displacement covered by block in the direction of displacement. Okay, so here if you will carefully see, so here if you will see the block, so this direction is force direction and displacement covered by the block in the direction of force is this shadow. Okay, so this displacement now we will calculate. So here force is here. Now when we will make a diagram, so this angle is 90°. So this is the displacement which occurs in the direction of force. Okay, angle between the force and the displacement is theta. Now what we will do, we need, see, theta, in front of theta we have perpendicular, 90 in front of hypotenuse and rest is base. Here we will use trigonometric formulas, which is Pandit Badri Prasad Har Har Bole Sona Chandi Tole. This you have done in math or you will do in math. Now carefully see, here you need what? Here you need base. As x we have to calculate displacement in the direction of force and hypotenuse work as a displacement. So these two things we need. Okay, so we need base and hypotenuse. Base and hypotenuse covered with this c. C here is cos theta. So in triangle ABC, cos theta is base upon hypotenuse. Cos theta remains same. Base value we have x and displacement hypotenuse we have displacement. So x value we got by cross multiply as s cos theta. Now carefully see what is work done. Work done formula we have, force and displacement occur in the direction of force. Force and displacement occur in the direction of force. So F is same. So x we got what? X value we have s cos theta. Okay. So here we got a formula, work done formula as W is equals to Fs cos theta. So this is the formula of work done when force and displacement are at some angle theta. So angle between force and displacement is theta. So work done formula we got Fs cos theta. So here s cos theta represent the component of displacement in the direction of force. This is displacement, but component of displacement in the direction of force is actually a s cos theta. Clear? So here if you will see, W is equals to Fs cos theta. So here work done is force and s cos theta represent here component of displacement in the direction of force. So this is the first expression and important expression for the numerical point of view when force and displacement not occur in the same direction. Now first thing we have done, we took displacement in the direction of force. Now next case we will see, here what we will do, we will take a force in the direction of displacement. In this case we will make a formula of work done when force we will take in the direction. So how we will take force? So carefully see, this angle is theta. So this is the force which I am taking in the direction of displacement. I am not taking the component of displacement now. I am taking component of force in the direction of displacement. Now this force and this displacement occur in same direction. F dash I am taking here. So here this is a perpendicular 90 degree. So this triangle again ABC. So these angles are vertically opposite. So this angle is also theta. So again theta, in front of theta we have a perpendicular, 90 in front of we have hypotenuse, and this is base. Okay. Now we need F dash we have to calculate, and F we have act as a hypotenuse. Again Pandit Badri Prasad har har bole, sona chandi tole. Now carefully see, base we required, hypotenuse we have. Again we will choose which formula? Cos theta. Cos theta is base upon hypotenuse. Base act as a, in this triangle base act as a F dash, which is the component of force in the direction of displacement, and hypotenuse act as a force. So F dash we got as F cos theta. So what is the formula of work done? Work done formula we have force which is in the direction of displacement into displacement. Here we are taking this displacement and force we are taking in the direction of displacement. F dash value we have F cos theta into S. So this is the formula we got, similar to the previous formula, that is Fs cos theta, or you can also write W as F cos theta S, which is already written. Okay, now carefully see, here work done is component of force in the direction of displacement, and this is a displacement. So if you will see the formula, so here we have W is equals to F cos theta S. So here work done is component of force in the direction of displacement into displacement. So in this two way you will derive a formula when force and displacement occur at some angle. But here good thing is that formula is same. In previous case we got Fs cos theta, in this case we got F cos theta. So magnitude wise they are same and direction wise also same. So here you will get a formula. This expression of work done is very important. Now we will see that work done is a product of magnitude of force, magnitude of displacement, and the cosine. Cosine means cos theta, cosine of angle between the direction of force and displacement. It means if this is a direction of force and this is a displacement, so angle between them is theta. So here work done formula we will got as W is equals to Fs cos theta. So this again I am telling, this formula is very important from numerical point of view. Okay. Now we have to see some note points. Note points we have, first is have force is a vector quantity. So force is a vector quantity means it depends upon both magnitude as well as direction. Displacement is also a vector quantity, but the product of force and displacement will give a work done which is a scalar quantity. How it is possible? Multiply of two vector quantities will give you a scalar quantity. Why? Because it is actually a vector dot product. Okay, this is little bit a part of +1, but still I am telling you one thing here, the force and displacement both are vector quantity, but dot product of vector quantity will give you a scalar quantity. So dot product of force and displacement will give you a scalar quantity, which is a work done. Okay, so this you have to remember, that force is a vector quantity, displacement is a vector quantity, but work done is a vector product of force and displacement, so it is a scalar quantity. Next we have types of work done, means how many types of work done we have. So basically we have three types of work done. First we have positive work done. What is the meaning of positive work done? Positive work done means when the angle between the force and the displacement is zero, means both force and displacement occurs in the same direction, so that is called positive work done. In positive work done, cosine of angle 0 degree is a 1 means a positive value. Next we have zero work done. Zero work done means when the angle between the force and the displacement is 90 degree. Okay, so angle between the force and displacement is 90 degree. So cos of 90 degree we have 0, which gives us zero work done. Last we have a negative work done. Negative work done means when the force and the displacement, okay, force and displacement both occurs in the opposite direction, so angle between them is 180 degree. So cos of 180 degree we have -1, means -1, which gives a negative work done. So we have positive, 0 and negative work done. So one by one we will see the example of these special cases. So first special case we have free fall of a body. So this is example of basically a positive work done. Why? Here force is acting in this direction, gravitational force mg, weight, and displacement occur in this direction only. So force and displacement both occur in same direction, so angle between them is 0 degree. So this is a, here theta is 0, means angle between them is 0. So this is the case of positive work done. Okay, so let's see the example of positive work done. We have in a free fall of body of mass m under the effect of gravity through some height h. So this is a case of positive work done. Next we have a coolie or a boy does a work on a load when he raises it up against the force exerted by a pulley and the displacement are in the upward direction. Now carefully see. For example, either it comes for a boy or for a coolie. Okay, so here the boy apply a force in the upward direction. Okay, and this dumbbell, this weight is having displacement in the upward direction. So both force and displacement occur in the same direction. So boy or a coolie does work done on a load which is against although the gravity, but force and displacement both occur in same direction, angle between them is 0. So as angle is 0, so this work is an example of positive work done. Next we have next special case. This is basically a rotational case. So here this we have done in the uniform circular motion. If you will remember, there is one centripetal force acting in this direction and displacement occur in this direction. So angle between them is 90 degree. So cos 90 we have, cos 90 degree we have 0. So this is a special case of zero work done. So here angle is 90 degree. So if I am taking a circle here, so this is the direction of force and this is the direction of displacement, angle is 90 degree. So this is an example of whole example of zero work done. Okay, so now for example, a man is standing with a heavy load on his head. Here angle, although it is 90, not 90 degree, but still this is a case of zero work done. Why? Because displacement is not occur here. So in this case displacement is not there. The person is standing at one place although he is applying a force on a body and there is no displacement of body occur. So this is a case of zero work done. Next case we have, this case we have seen in previous example. A man walks on a horizontal ground while carrying a load on his head or on the side. No work is done against the gravity. Why no work is done against the gravity? Because according to gravity, its weight acting in the downward direction. Weight, which is mg, act as a force acting in the downward direction, and displacement occur in the forward direction. So angle between them is 90 degree. So we know that cos 90 we have 0, and work done formula we have Fs cos 90. Although force is there, although displacement is there, but cos 90 is 0. So magnitude when multiplied with 0, it give a 0 value. So here, because displacement of load is normal means 90 to the direction of force of gravity, which is vertically downward. So that's why this is an example of 0 work done. Here theta is 90 degree, so work done is 0. So here you will see the condition for a work done by a force to be 0. Under what condition? Under two conditions when force is 0. First condition we have when work done is 0. When there is no displacement, then work done is 0. Second, when the displacement is normal to the direction of force. When the angle between the force and direction is 90 degree, that examples come under the 0 work done. Okay. Next special case we have when a person throw a ball in the upward direction. So in this case, displacement occur in the upward direction and weight of this ball is acting in the downward direction. Okay. So angle between force and displacement here is 180 degree, and cos of 180 degree will give you -1. It means this is a case of negative work done. So person throw a ball, or a boy throw a ball in the upward direction. So due to the gravity, this is a case of negative work done. Let's see one more example of negative work done. When a body moves on a rough surface, as this body displaces in this direction, displacement occur in this direction, and force, frictional force applied in this direction. So this force and displacement are occur opposite to each other. So angle between them is 180 degree. Again, it is an example of a negative work done. Okay. Now let's see the graph between force versus displacement. So before drawing the graph between force versus displacement, these are basically two cases. So one by one we will see the cases. First case we have when force is variable. Force is variable means what? For example, I am applying a force on this body. Initially force is 0, then force is 1, 2, 3, and increasingly means keep on increasing. Okay, so this is an example of variable force. Next we have when force is fixed. Force is fixed means, for example, on a block I am applying a 50 Newton force. Now this displacement occur in the direction of force, but 50 Newton is remain constant. So this is an example when force is fixed. Now let's see the example. When force is variable, initially we are applying less force, then force is keep on increasing. So here how graph will form, carefully see. So here I am taking y-axis and x-axis. On y-axis I am taking force, and on x-axis I am taking displacement. Here force is variable means initially force is having less value like 0, then displacement keep on increasing and force is also keep on increasing. So this graph is basically like this. Okay, so this is a graph where initially force is 0, displacement is 0. Force's value is increasing, displacement is also increasing. So here we have to see one thing, that in this graph the area under this curve will give you the formula or value of work done. So area under force displacement graph will give you work done. Now if I am talking about this force, I am talking about the force is variable, case when force is variable. So this is a area is 1/2 base. base we have displacement, and height we have here force. Okay, so work done when force is variable, we have 1 by 2 F into x. So this is a formula of work done when force is variable. And when next we have when force is fixed, when the value of force is fixed. For example, 50 Newton force is applied on a body and 50 Newton is remain constant. So force is fixed and displacement is increasing. So here how we will make a graph. So force is in the y direction, displacement x direction. So here force value is fixed. For example, 15 Newton, force value is fixed and displacement is keep on increasing. So how we will make a work done formula? For example, area we will take here, this area we are taking. Okay, so now how we will make, so this is the area, this is basically a rectangle area. What is the formula of area of rectangle? Base into height. Base we have x, height we have x. So work done we will got here F into x or F into s. Now carefully see, we are using the formula work done as Fs. So what is the assumption we are taking in order to use the formula? The assumption is that when force is fixed, means force is keep fixed on a body, it will not changing. Then only we are using work done as F into S. Clear? Next we have work done by force of gravity. For example, this ball is placed on an incline. So what will happen after some time? The ball will move in the downward direction. So here we have some dimensions of this inclined plane. Now carefully see and tell me which force keep this body to move in the downward direction. So which force is acting? So they are talking about force of gravity, means its weight is acting, which is due to the gravity. So weight is acting in the downward direction. Okay, so this ball is moving in this direction. Now tell me, we know we have to calculate the work done. Work done is force into displacement, and displacement occur in the direction of force. We have three dimensions A, B and H. Out of three dimensions, which dimension we will take in order to find the work done in this case? So many people think that here we will take A as a displacement because body move in this direction. So this displacement we will take, but A displacement we will not take. Why? Because force is due to gravity. Force is due to gravity means work done, if you will calculate, weight is acting due to gravity in the downward direction, which is a force, and in this direction displacement is h. Okay, in the direction of force displacement is h. So work done we have force is equals to m into g, and displacement in the direction of force we have h. So work done due to gravity on a body we have mgh. This formula you have seen as a potential energy formula, which is derived from the same relation that gravity force is acting on a body, and body moves certain distance, and that distance we are taking it as a vertical height. So if someone asks work done by a force of gravity, then that direct formula we will use as W is equals to mgh. Okay. Next we will see the SI unit of work done. So SI unit of work done, we have to remember this. Work done is equals to force into displacement. Force SI unit is Newton, displacement meter. So this work done of SI unit means work done SI unit is joule. So 1 joule we have 1 Newton into 1 meter. Clear? Next we have, so what is this meaning? It means that when 1 Newton force is applied on a body and body displaces 1 meter. So when 1 Newton force is applied and body displaces 1 meter, that is called a 1 joule work done. Clear? So what is 1 joule work done? When force of 1 Newton displaces a body through a distance of 1 meter, or you can also write displacement of 1 meter, that work done is called 1 joule. Now let's see the CGS unit of work done. CGS unit of work done. Force CGS unit is dyne, displacement CGS unit is centimeter, work done CGS unit is erg. So okay, so 1 erg is 1 dyne into 1 centimeter. So here 1 erg work is defined as when 1 dyne of force is applied on a body and body moves a displacement of 1 centimeter, that is actually a 1 erg work done. So what is the definition? Carefully see. When a force of 1 dyne displaces a body through a distance of 1 centimeter, that is a 1 erg, which is a CGS unit of work done. Now let's see the relationship between joule and erg. So 1 joule we have 1 Newton into 1 meter, and 1 erg we have 1 dyne into 1 centimeter. Now carefully see what is the relationship between Newton and dyne. So in 1 Newton basically we have 10 raised to power 5 dyne, and if I'm talking about meter and centimeter, this we know 1 meter is 100 centimeter. So now put the values. 1 joule as 1 Newton we will put as 10 raised to power 5 dyne, and 1 meter we will put as 100 centimeter. Okay, now if you will see the 0, 10 raised to power 5, 6 and 7, 10 raised to power 7 dyne centimeter, okay, which is equals to 1 joule. 1 joule you can also pronounce. So 10 raised to power 7 dyne centimeter is equals to erg. Okay, so this is a relationship between the joule and erg, that is 1 joule is 10 raised to power 7 erg, and this is very important relationship. Derivation is also very important. So here we have 1 joule is 10 raised to power 7 erg. Next we have to see the concept of power. So in whole scenario you have seen when force is applied on a body and body displaces in the direction of force, but the concept of time we have not mentioned, in how much time we have to do that work. So this concept of time comes under power. So let's see the definition of power. Power is that rate of doing work. Rate means with respect to time. So basically the formula of power is work done per unit time. It means that when a person is doing more work done, then it is having more power, and when a person is doing work done in less time, then it is having a more power. So power is work done per unit time, and power is a scalar quantity. It means that power does not depend upon the direction, it depends upon work done, and it depends upon time. Work done is a scalar quantity, does not depend upon direction. Time is a scalar quantity, again does not depend upon direction. So scalar upon scalar will give you a scalar quantity. So power is a scalar quantity, we have to remember this. Okay, now we will see, for example, we have two elephants. Let's take the example of power with from elephants. So here two elephants we have. Now let's see the motion. Now two elephants A and B, both having cover same displacement in equal time, means both cover same displacement in equal time. So now tell me in which case work done is more. So now displacement is same, okay, but weight of this elephant is more than weight of B elephant, means force is greater. So work done by A is greater than work done by B. This represent work done, okay. Weight is also greater. Now if I am talking about the time taken by both the elephant is same. So in which case power is more? Power is equals to work done per unit time. So time is same. Work done by this elephant is more than, means fat boy has to apply more efforts in move cover a same distance as the thin boy covers. So here work done by this elephant is more, and they are covered in same time. It means it only depend upon the work done, time is same. So power of this A elephant is more than power of this B elephant. Clear? Now let's see the same size elephant. Now let's see carefully. Here if you will see the motion carefully, both elephant cover same displacement. So displacement in this case is same, and both are having same mass, same force. Okay, so both are having same work done, but one thing is different, that is time taken by this elephant is less. Okay, sorry, time taken by A elephant is less and time taken by B elephant is more. It means that power is equals to work done per unit time. More is the time, less is the power. So which elephant is having more power? Which moves faster? So it means that power of A elephant is more than power of B elephant. So here from this example it is clear that more is the work done, more is the power, more is the time, less is the power. Clear? So this is the example of power. Next, relationship between power, force and velocity. We know that power is equals to work done per unit time. And what is the formula of work done? Force into displacement. Okay, time. So displacement per unit time is called velocity. So displacement per unit time will give you velocity. So power we have force into velocity. So this is a derivation or relationship between which is important for numerical point of view. So power we got as force into velocity. Clear? Next we have units of power. Power unit, if I am talking about, work done having unit joule, time is having second, power unit is watt. So here 1 joule, what is 1 watt also if I am talking about, power unit is watt. Okay, this joule work done is joule or joule. Next time we have in second. So 1 watt is defined as when 1 joule of work is done or 1 joule of work is done in 1 second, the power spent is said to be 1 watt. So this is a SI unit of power. And if I am talking about SI and CGS unit, watt we have SI unit and CGS unit we have erg second. How? Carefully see. Power is equals to work done per unit time. If I am talking about CGS unit, then CGS unit work done we have erg and time we have second. So erg per second we have a CGS unit. Now if I will draw the relationship, 1 watt we have 1 joule over 1 second. So joule per second. Now joule per second, in 1 joule we have 10 raised to power 7 erg, which we have already derived, and second is same, remains same in CGS. So it means 1 watt we have 10 raised to power 7 erg per second. So this is a relationship between SI and CGS unit of power. So this is the relation between SI and CGS unit of power. Next we have one most important relationship, that is a horsepower. Horsepower value you have to remember, which this horsepower we are using in the case of cars. In automobiles, power we are calculating in horsepower. So horsepower we have 746 watt, or when you will divide it by 1000 you will get it in kilowatt. So 0.746 kilowatt. Clear? Next we have energy. So what is energy? Let's see the definition of energy. Energy, we have energy of body, its capacity to do a work or ability to do a work. So this is the definition of energy. Means how much energy or how much capability you have to do a work, that is actually a energy. But numerical point of view, SI unit point of view, energy and work done is same. Clear? From all point of view, energy and work done is same. So now it is a scalar quantity because work done is a scalar quantity. Here it is an important point. When there is no work done, no transfer of energy takes place. Means for example, I am rotating a stone. Okay. While rotating a stone, force and displacement occur in the 90-degree, means work done is 0. So in the rotational motion, when work done is 0, then there is no transfer of energy takes place. We know that energy can be transferred from one point to another point. Conservation of energy states that energy can neither be created nor be destroyed, but it can be transferred from one point to another point or one form to another form. But here when work done is zero, then we can't transfer the energy in that case, and one example is a circular motion. Clear? Now we will see the units of energy. Energy in another way you can say, carefully see, power is equals to work done per unit time. So work done we have power into time. Okay. This work done act as energy, and this power, what is SI unit of power? Watt. What is SI unit of time? Second. Or any way you can use. You can also use kilowatt or. So that's why power into time unit will give you a energy unit. Okay, power into time unit will give you a energy unit. And one more important unit of energy which is equal to the work done, that is a joule or joule. Okay, so joule is the SI unit of energy, you can say that. These are other units of energy. Now what is our work? Our work is to calculate watt hour into joule, means to convert watt hour into a joule. Now how we will do? Carefully see, watt into hour. So watt is remain same, hour value we have in 1 hour. How many seconds are there? 3600 seconds. So we have 3600, 3600 seconds. So 3600 watt second. So what is the value of watt second that we have to see? We have power is equals to work done per unit time. Power is watt, this work done is joule, and time is second. So watt into second we have joule. So this whole value is converted into joule. Clear? So this we got. Now divided by 1000, you will get 3600 divided by 1000. So this become a kilojoule. So we got as 3.6 kilojoule. It means that 1 watt hour is equals to 3.6 kilojoule. Clear? Now how to convert 1 kilowatt hour into joule? Again same, it is 1 kilowatt into 1 hour. Okay. Now 1 kilowatt we have 1000 watt, and 1 hour we have 3600 seconds. So this become 3600 into 1000 watt second. Watt second it is joule, and it is 1 2 3 4 5. 36 into 10 raised to power 5 joule. This is one value. Again what we will do, we will convert it into megajoule. Divided by 10, multiply it with 10. 10 raised to power 5 remains same. So this become 10 raised to power 6, and this become 3.6. So 3.6 into 10 raised to power 6 joule or 3.6 megajoule. So here if we will see the result, 1 watt hour is equals to 3.6 into 10 raised to power 3 joule or 3.6 kilojoule, and 1 kilowatt hour we have 3.6 into 10 raised to power 6 joule and 3.6 megajoule. Clear? Next we have calorie. So what is 1 calorie? This definition is very important also from other chapter point of view. So calorie is defined as amount of heat energy required in rising the temperature of 1 gram of water by 1 degree Celsius. What is the meaning of this? Carefully see. For example, I have 1 gram of water here. Okay, for example, this mass is 1 gram, and its initial temperature is, for example, 70 degrees Celsius. Okay, initially it is at 70 degrees Celsius, or less value you can take. For example, we are taking 20 degrees Celsius. Okay, so now when I'm heating this from 20 to 21 degrees Celsius, okay, 20 degrees Celsius to 21 degrees Celsius, if I'm heating this water, so it will absorb some heat. So the amount of heat absorbed by 1 gram of water to rise its temperature by 1 degree Celsius, that absorption of heat is called 1 calorie. Again just see, amount of heat energy, how much the heat energy required by 1 gram of water to raise its temperature through 1 degree Celsius from 20 to 21 or from 25 to 26, from 1 degree Celsius, how much heat is required? That is called 1 calorie. And in case of water, for 1 gram 1 calorie we have 4.186 joule, and if I'm talking about 1 joule we have 0.24 calories. Both values are very important, and this value is most important. Clear? Next we have what is electron volt. So this definition is actually very important. 1 electron volt is the energy gained by electron when it is accelerated through a potential difference of 1 volt. For example, this is a wire and it is attached with the battery. Now carefully see, this battery creates a potential difference of 1 volt. Okay, so this is positive, this is negative. So electron under the influence of this battery will accelerate toward the positive terminal. So energy gained by this electron under the influence under 1 volt battery, that is called electron volt. So 1 electron volt is energy gained by an electron when it is accelerated through a potential difference of 1 volt, and we know that potential difference is work done per unit charge. So work done in this case, we potential difference into charge. A potential difference we have 1 volt. Charge it is an electron charge we have 1.6 into 10 raised to power minus 19 coulomb. So work done SI unit is joule. It means that in 1 electron volt we have work done is equals to 1.6 into 10 raised to power minus 19 joule. Clear? So this is very important. Next we have different forms of energy. So in this part we will see how many types of energy exist in the nature. We will see the different forms of the energy. So first energy we have a mechanical energy. Mechanical energy is divided into two parts. First is potential energy, second is kinetic energy. What is the meaning of potential energy? Potential energy is the energy possessed by a body at rest in its change position or change in size and shape. What does it mean? Carefully see. For example, when ball is there and this ball is at some height from the ground, so energy is stored in the body, that is called potential energy. And we have one rubber band. When we stretch the rubber band, it get deformed and energy is stored in the rubber band to come back to its original position. That is called again a potential energy. So energy possessed by a body which is at rest, and it is due to its change in position or change in size and shape. And what is a kinetic energy? Kinetic energy is a energy possessed by a body due to its state of motion. Here you have to remember, potential energy is at rest and kinetic energy is this energy possessed by body due to motion. For example, when stone is there and when stone strike a glass, it breaks the glass. How it will able to break the glass? Because it is having some kind of energy which it transfer to the glass and the glass get breaks. So it means that the energy possessed by a body due to its motion, this is called kinetic energy, and sum of potential and kinetic energy will give you a mechanical energy. Next we have to see forms of potential energy. First we have seen mechanical energy is of two types, potential and kinetic. Now potential is further divided into two types. First we have a gravitational potential energy and second we have a elastic potential energy. What does gravitational potential energy means? Gravitational means related to gravity. Each and every body is attracted toward the earth because of force of attraction. So when it is moving away from earth, some form of energy is stored in a body. That energy is called gravitational potential energy. And what is elastic potential energy? We have to understand the meaning of elasticity. Elasticity means to come back or to regain its original position. For example, this is a spring. When I apply a force on the spring get compressed. Now even though when I remove the force, then the spring automatically come back to its original position. It means that some form of energy is stored in the spring which makes the body to keep or come back to their original position or original shape and size. So this is called elastic potential energy stored in a body when we are actually changing its shape or size. So coming back to its original position after the removal of external force, this property is called elasticity. Clear? Next we have to see what is gravitational potential energy in detail. Carefully see. Gravitational potential energy, we know that each and every body is attracted toward the earth. Okay, some force is acting by the earth. Why? Because two bodies attract each other. So here earth attracting this ball, but there is some distance, beyond which earth gravitational field does not exist. For example, after this reason earth not able to attract the body toward itself. So that distance from the earth at which the gravitational energy or gravitational force by the earth is zero, that distance is called infinite distance. Okay, this is called infinity distance or infinite distance. Now the work done by the earth in bringing a body from infinity to at that point, at any point, this is called work done by earth. This is also called gravitational potential energy. Okay, when the body is moving upward, then gravitational potential energy will increase. When it is moving downward, then gravitational potential energy will decrease. Now see the definition. Gravitational potential energy is basically the amount of work done by the force of attraction of earth. The force of attraction of earth is doing a work done on this body, and it is bringing the body from infinity to at that point. So this is basically a gravitational potential energy. Clear? Next we have gravitational potential energy expression. So for example, I am making a body, I am keeping a body to keep at some height, means I am taking a body from the ground and taking it to some height. Some form of energy is stored in the body. So what is the nature, what is the magnitude of this energy, we have to calculate. So this body is having some force acting on the body in the downward direction, which is F is equals to mg. This is also called weight of the body. This weight is occur because of the earth. Earth is attracting this body toward itself. So that's why here force we have m into g, weight. Next we have, it is having some height. Okay, so what is gravitational potential energy? Work done by the earth. What is work done? Force into displacement. Force we have mg and displacement is h. So energy stored by the in the body due to the gravitational field, that is called potential energy. So potential energy formula we got as U is equals to mgh. So here gravitational potential energy formula we have U is equals to mgh. Here m SI unit is kg, G SI unit is meter per second square, and H SI unit is meter, and whole U, this is energy. Energy is actually a work done, so its SI unit is joule. So this is the whole expression of gravitational potential energy at some height. Next we have elastic potential energy. What is elastic potential energy? Carefully see. For example, I have an elastic body. Elastic body means when I apply a force on a body, it gets deformed. Deformed means change in shape or size. Okay. When I remove a force, it has the ability to come back to its original form, come back to its original shape and size. This property of body after removing the force to come back to their original shape and size, that is called elasticity. Okay, so when I apply the force, the body get deformed. Some type of energy is stored in a body, that energy is called elastic potential energy. Okay, so if I'm talking about what is elastic potential energy, the energy stored in the deformed state, whatever the energy stored in the body due to its deformed state or due to its change in shape and size of body, that energy is called elastic potential energy. So two type of potential energy we have seen: gravitational potential energy due to the earth attraction force and elastic potential energy. Next we have kinetic energy. What is kinetic energy? Now instead of focusing on this bow, now focus on this arrow. The energy possessed by a body due to its motion, energy possessed by a body due to its state of motion, this is actually called a kinetic energy. So energy possessed by this arrow, okay, this energy possessed by this arrow which is in motion, it is having kinetic energy. Okay, like the expression we have done from the gravitational potential energy, let's make a one expression for kinetic energy. Let's see the expression of kinetic energy, in which a body which is moving with some initial velocity is stopped by a force F, creating a retarding force. It acts as a retarding force. So initially this body is having some initial velocity v, final velocity of this body is 0, it is having some mass and stopped by some retarding force. So acceleration in this case is actually a retardation, negative of acceleration is produced and displacement covered by a body is s. Now we have to derive the expression of kinetic energy. Before that we should know what is kinetic energy. Kinetic energy is the energy required by a body to come to rest if it is moving with some initial velocity. Means a body is moving with some initial velocity, how much force is required, how much work is done on the body to stop the body, that is called kinetic energy. So we have to calculate work done, which is force into displacement. Force, we have mass into acceleration into displacement. Now we need the expression in velocity, so we will use the third expression of Newton's law, that is v square minus u square is equals to 2as. Final velocity we have 0, initial velocity we have v square, 2 acceleration we have minus a, it is retardation, and displacement s. So minus v square is equals to minus 2as. So here we got v square as 2as. So from here calculate the value of s as v square by 2a. Put value here. So here displacement we have v square by 2a. So a and a cancel out. Work done we got here as half mv square. So this work done is actually a work done to stop a moving ball. So this is actually a kinetic energy, which is half mv square, and kinetic energy is denoted by the symbol k. Clear? Now let's see again the definition. So definition we have: kinetic energy possessed by a moving body is equal to the amount of work which the moving body can do. It is the amount of work which a moving body can do before coming to rest. So before coming to rest, whatever is the amount of work done we have calculated, that is a kinetic energy. So we have calculated kinetic energy as half mv square. Now let's see what is the effect of changing mass and velocity of a body. For example, a body is having some mass m moving with velocity v. Clear? Now it is having some kinetic energy k, which is half mv square. Now if I increase the mass to 2m and velocity remains same, what is the change in the kinetic energy? What is the new kinetic energy in terms of old kinetic energy? So new kinetic energy k dash we have 1 by 2 m become 2m v square as it is. So here it become 2 times half m v square. This 2 is coming out and this is the old kinetic energy. So 2k. It means that new kinetic energy we have double times the old kinetic energy by increasing the mass to twice of its value. Now do the same expression for velocity. Means, for example, a body is having mass m moving with some velocity v. Now keeping the mass constant and increasing the velocity to 2v. So initially it is having some kinetic energy k, which is half mv square. Now calculate the kinetic energy. New kinetic energy k dash we have half m, v we have 2v. So 2v whole square we got 1 by 2 m 2 square into v square. 2 square take it out from the bracket, which become 4 and half mv square. So this half mv square is again a kinetic energy 4 as it is, and it is k dash. So new kinetic energy will become 4 times the initial kinetic energy. It means that when mass we are getting doubled, kinetic energy will become double. When velocity we are getting double, then kinetic energy become 4 times. So the effect of velocity is more on the kinetic energy as compared to the mass effect. Clear? Now let's derive the relationship between the kinetic energy and momentum. We know that kinetic energy formula as half mv square, and momentum, which is denoted by p, formula is m into v. From here momentum formula, calculate the value of velocity. So velocity we have p by m as velocity. Now put the value of velocity in the expression of kinetic energy. So here we have half m, velocity we are writing it as p by m square. So p by m square, it becomes squaring on both numerator and denominator, p square by m square. Okay, so 1 by 2 m, p square is as it is, write m square as m into m. So cancel m and n from numerator and denominator both. So here we got p square by 2m. So kinetic energy we got as p square by 2m. Multiplying 2m this side, this is also one expression. One more expression we can make, that multiplying 2m on that side. Here we have p square. So p become root on the another side. So under root 2 km. So this is the expression of momentum with the kinetic energy. So it is the exact relationship between kinetic energy and momentum, which is very important from the numerical point of view. This is the expression of momentum with mass and kinetic energy. Now let's discuss a case in which we have two bodies, A and B body. So it is having some mass ma, momentum pa, and kinetic energy ka. Another body B is having mass mb, momentum pb, and kinetic energy kb. Now we will find the ratio of momentum of these two bodies. So here pa we have under root 2 ma into ka, and pb we have, that is momentum of b body, we have under root 2 mb kb. Now what we will do, just divide these two equations. So pa over pb we have, separate this root, under root 2 under root ma under root ka over under root 2 under root mb over under root kb. So from here we will get as pa over pb is equals to under root ma over mb into under root ka over kb. Clear? So this is the expression which is very important for numerical point of view, in which they can give you the two bodies and you have to compare their momentum, their mass, their kinetic energy, and if one thing is constant you can also cancel it out. So here we will discuss some relation based on this. Again, for example, we have A body and B body, in which both A body and B body is having mass mb and mb, in which ma is greater than mb. Kinetic energy, for example, we have same, and momentum relation we have to calculate. Okay, pa and pb, we have to see which body is having more momentum and which body is having less momentum. So formula we have pa over pb is equals to under root ma over mb and ka over kb. Clear? Now we have ka and kb both are same, so it is cancel out. So PA over PB is equals to under root MA over MB. It means that which body is having more mass? So MA is having, A body is having more mass. So MA is greater than MB. As MA is greater than MB, so this whole ratio is greater than 1. So if this whole ratio is greater than 1, this ratio is also greater than 1. It means mass and momentum are directly proportional. So PA is greater than PB. Clear? Now see the next expression in which two bodies A and B. Now this time MA, MB. Again MA is greater than MB. Kinetic energy we have Ka and Kb means different. This time momentum is same. Okay, momentum we have same. Expression we have same. Pa over Pb is equals to under root Ma over Mb into Ka over Kb. This time momentum is same means this part is cancel out. So here Ka and Kb cross multiply or mass you can send that side. It become Mb over Ma reciprocal. Okay. So Ka over Kb this side and root Ka over Kb. Now carefully understand. Now mass of A body is more than mass of B body. It means denominator is more. Denominator is more. So this whole part is less. So this whole part is less. It means kinetic energy of A will decrease from B. Now here mass more, it means kinetic energy will decrease. This is the expression only possible. This thing is possible only when momentum is constant. Otherwise, when kinetic energy and mass are directly proportional, when mass increases, kinetic energy decreases. But here when mass increases, kinetic energy decreases. It means that this case is possible when momentum is constant. Otherwise, this case is not possible. Clear this part? Next we have work energy theorem. So what is the definition of work energy theorem? Work energy theorem states that increase in kinetic energy of a moving body is equal to the work done by a force acting in the direction of moving body. What does it mean? Carefully see. For example, a body is moving with some initial velocity. Okay, it is having some initial kinetic energy. By applying a force, we are increasing the speed of that body. So when we are increasing the speed, we are doing some work done in increasing its speed. So that work done is equal to change in kinetic energy or increase in kinetic energy. Now let's understand with the example. For example, a ball is moving with some velocity, initial velocity u. After applying some force, its velocity will increase. Okay, so it become v. Okay, so initial velocity of this body is having u, final velocity we have v. And kinetic energy, if I am talking about, initial kinetic energy of this ball is having half mu square. By applying some force, its velocity will increase. So final kinetic energy we got it as half mv square. So how much is the increase in kinetic energy? So increase, if I am talking about increase in kinetic energy, we have final kinetic energy minus initial kinetic energy. Final kinetic energy we have half mv square minus initial kinetic energy we have half mu square. Now let's calculate the work done in this case. So here we are applying some force which moves a body to cover some displacement s, okay, by producing an acceleration a. So F we have force apply, we have mass into acceleration. So work done in this case we have force into displacement. Force we have mass into acceleration, and displacement in this case we have s. Okay. Now from the equation of third equation of motion, v square minus u square is equals to 2as. V square we have final velocity as v square, initial velocity u square, 2as. So from here let's calculate the value of displacement as v square minus u square by 2a. Now put the value of displacement here. So mass into acceleration, v square minus u square over 2a. So cancel it out. We got as 1 by 2 m v square minus u square. Now multiply, work done we got it as 1 by 2 mv square minus 1 by 2 mu square. Now carefully see, this is the work done to increase the kinetic energy, and this is increase in kinetic energy. Have you seen any correlation? These are both equal. It means that work done on a body to increase its kinetic energy is same. So increase in kinetic energy of a moving body is equal to the work done. Increase in kinetic energy, which is final kinetic energy minus initial kinetic energy, is equals to the work done which the force is doing to increase its velocity, otherwise increases kinetic energy. So this whole thing is actually a work energy theorem. Clear? So this is the expression of work energy theorem, in which work done on a body is increase in kinetic energy. Increase in kinetic energy here, half mv square is final kinetic energy and half mvu square is the initial kinetic energy. And final minus initial kinetic energy is increase in kinetic energy, which is equals to the work done. Now we have seen in the previous part forms of potential energy. Now here we will see the forms of kinetic energy. So kinetic energy forms depending upon the type of motion. For example, we have basically three types of motion. When body is moving in a straight line, that is called translational motion, and kinetic energy related to that is called translational kinetic energy. Second, we have when body is in rotational motion, the kinetic energy associated with the body, that is a rotational kinetic energy. Third, we have when the particles are vibrating about their mean position, the energy associated with the body is called vibrational kinetic energy. Next, we have different forms of energy. Instead of potential, kinetic and mechanical, we have another different form of energy. After watching all these energies, we will see the conversion of one energy to another. First, we have solar energy. The energy radiated by sun is called solar energy, and there are some devices which collect this solar energy. These are called solar devices. Solar panels, we have different solar cells, and we have solar furnaces. So these are devices which concentrate or which collect this solar energy. Next we have heat energy. So heat is a form of energy which is released on the burning of natural gases like coal, petrol, wood gases, or fossil fuel, we can say that. Next we have light energy. So energy which is used to see the object either through sun or through tube light, any energy through which we are able to see the other things, that is called a light energy. Next we have chemical energy. So chemical energy, the energy possessed by fossil fuels. In the fossil fuels, carbon is there which on burning produce energy, such as coal, petrol, natural gases. These are having some energies which is in the form of chemical energy. So after that we will use in different form also. Next we have hydro energy. Hydro means related to water. So energy possessed by fast moving water, that is called hydro energy. Even the water is standing, that is comes under the potential energy part of hydro energy, and moving water comes under the kinetic energy part of hydro energy. Next we have electrical energy. So electrical means related to electrons. So the energy possessed by the movement of free electrons. When electrons are freely moving, then whatever the energy possessed, whatever energy is created by this free electron, that is called electrical energy, which we have seen in case of batteries. Next we have nuclear energy, very important. This is the energy due to loss in mass. When the mass will lose, when there is a process of nuclear fission and nuclear fusion. What is the meaning of nuclear fission? Carefully listen. Nuclear word is related to nucleus. Fission means breakdown, fusion means combine. When nucleus is breakdown into parts, into smaller parts, the large amount of energy is released, and vice versa also. If the two nucleus, or if some part is joined in the nucleus, then also energy is released, that is comes under the nuclear energy. Next we have geothermal energy. In the earth crust, in due to the nuclear disintegration in the interior part of the earth, there is lava and magma which touch with the water body and make the water body too much hot. Okay, so this hot water is used by power plant to generate energy. So geothermal energy means energy released in the nuclear disintegration in the interior part of the earth, which is deep inside the earth. Next we have wind energy. Wind energy, as the name clear, the energy possessed by fast moving air. When air is moving fast, then whatever the energy is associated with fast moving particles, fast moving air particle, that is called wind energy. How we are using it, that is the another case. Next we have sound energy. So what is sound? When a vibration is produced, so whatever the thing we are hearing with the help of ear, that is a sound. So a vibrating body possesses the energy, that energy is called sound energy. Next we have magnetic energy. So magnetic energy is energy possessed by a magnet due to which it can attract the iron filling. So magnetic energy is a type of energy through which with the help of that energy the magnet can attract the iron pieces. So it is a magnetic energy. Next we have mechanical energy. Mechanical energy, we have basically two types, but here energy possessed by a body due to state of rest or of the motion. Either the body is at rest and from some height, that is a potential energy, or it is moving. Both rest and motion types of energy comes under a mechanical energy. Next we have conversion of energy from one form to another. So here in this case I will give you some examples. That examples you have to see clearly and tell me which one form of energy is converted into another. Like first example we have a free fall. When body is moving freely fall, then which one type of energy is converted into another? Initially it is having gravitational potential energy, then it come to motion. So here gravitational potential energy is converted into kinetic energy. Next we have when we stretch a bow, okay, and when we are stretching the bow, it give transferring the energy to arrow, and arrow is moving in the forward direction. So when we are stretching the bow, we are applying the force on the bow, it gets stretched. So which form of energy is stored in the bow? That is a elastic potential energy, and it give energy to the arrow, arrow is moving, so it is a kinetic energy. So in this case elastic potential energy is converted into kinetic energy. Next we have when ball is fall on a spring, it falls down, spring get compressed, and again it is bounced back. Now carefully see in this example, initially the ball is having which form of energy? Potential energy. After this potential energy is converted into kinetic energy. When this ball is strike on the spring, spring get compressed. As the spring get compressed, elastic potential energy is stored. So after elastic potential energy, again it give energy to the ball, and ball is moving in the upward direction. So here we have first gravitational potential energy converted into kinetic energy. Okay, gravitational potential energy converted into kinetic energy. After that the compression of spring, elastic potential energy it given to the ball, and ball again gains the kinetic energy. So this is the whole conversion. Next we have, in this case we are giving electricity and fan is rotating. So rotating is also a type of a kinetic energy. So here electrical energy is converted into, you can also write kinetic energy, or you can also write mechanical energy related to motion, related to rest or motion, you can write mechanical energy. So electrical energy is converted into mechanical energy. Next we have, here we are giving electricity and it is a heater. So here electrical energy is converted into heat energy, electrical energy converted into heat energy. Next we have, this is actually a power plant. So in the power plant we are giving heat and we are generating electricity. So heat energy to electrical energy. Okay, coal is burned here, so heat energy is converted into electrical energy. Next we have, here we are giving electricity and it is a loudspeaker, sound is produced. So in this case electrical energy converted into sound energy. Clear? Next we have, this is a microphone. Here we are speaking in the microphone and the signal is converted into electrical energy and then we are using it in the various forms. So here in case of microphone, sound energy is converted into electrical energy. After that we can attach to a loudspeaker or any other part, that is our choice. But here first part of the microphone work is to convert sound energy into electrical energy. Next we have, here we are charging the battery. How we will charge the battery? By giving some electrical supply. So by giving the electrical supply we are charging the battery. Which form of energy is stored in the battery? That is a chemical energy. So in this conversion, while charging a battery, we are giving electrical energy and we are getting chemical energy. So electrical energy to chemical energy. And while discharging means we are using our phones. So as we are using our phone is having battery which is having some chemical energy stored in it, and that chemical energy is converted into electrical energy. So during discharging of battery, chemical energy is converted into electrical energy. Next we have burning of candle. Burning of candle we have, so in the candle we have a chemical energy, and this chemical energy we are getting as a two parts. Here heat also, here light also. But the main purpose of the candle is to give the light. Okay. So here we will see the main part, that is chemical energy stored in the wax is converted into light energy. Although heat part is there, but that heat part we are not using in case of candles. For that we are using coal, petrol and other thing. We are using light, we are taking light as a major part from candle. So here we will write chemical energy to light energy. Next we have photosynthesis process. Here photosynthesis process, sun is giving energy to the plants and plants make their own food. This is a photosynthesis. So in this case light energy is converted into glucose. Glucose is a chemical. So light energy is converted into chemical energy. These all are examples, very important. Next we are giving electricity and bulb is glowing. So bulb is giving light, so electrical energy to light energy. Next we have a sun is there and sun is radiating their energy. Here it is a solar panel which convert this light energy to a electrical energy. So which conversion is there? That is light energy to electrical energy. Next we have a rocket. So in the case of rocket motion, heat is there in the rocket and rocket is moving. Moving means mechanical energy. So here heat energy is converted into mechanical energy. Burnt gases are there. As the gases are burnt, which gives release too much heat. When it release too much heat, it is moving in the forward direction. So in case of rocket motion, heat energy is converted into mechanical energy. Next we have burning of coal. Now carefully see, in case of burning of coal we are getting both heat and light. But in case of coal, heat is our major part, light is not our major part. That is a major part of candle. So here we will write chemical energy stored in the coal. So coal is converted into heat. So chemical energy converted into heat energy. Next we have, for example, car we have. So in the car, which thing we are using? Petrol. So petrol, which energy is there in the petrol? Chemical energy. And car is moving, which is a mechanical energy. So here chemical energy is converted into mechanical energy. Next we have a battery, a solenoid or a electric bell. So here electricity we are giving and we are getting magnetic effect. Okay, electricity we are giving, so in the electric bell also we are getting magnetic effect, that's why it is attracted and strike with the gong. So here electrical energy is converted into magnetic energy. We have a note point which states that whenever mechanical energy changes into other forms, it always in the form of kinetic energy, that is the stored potential energy first changes into kinetic energy and then kinetic energy changes into another form. What is the meaning of this? Carefully see. For example, a kinetic energy is there in the water, okay, which rotate the turbine and it generates electricity. So in this case what is actually happening, first stored form of mechanical energy, which is a potential energy, is first converted into kinetic energy and then kinetic energy transform into another energy. So this is very important note, that whenever there is change in mechanical energy to other form, it always in the form of kinetic energy, means potential energy directly cannot converted into another form, first it changes into kinetic energy and then any other form can takes place. Clear? Next note point we have, while transformation of energy from one form to another desired form, the entire energy does not change into desired form. Means when one form of energy we are converted into another desired form, all 100% of energy transformation will not takes place. Why? Because some part of energy, that is undesirable energy, is also produced, that is in the form of heat, friction, sound, etc. For example, the part of energy which is not available to us, that is called undesirable energy, or we can say that degraded form of energy. In case of moving of a car or motion of a car, we are giving a petrol or we are giving a chemical energy. So whole chemical energy is not converted into only mechanical energy, motion of a car, in which some heat, some energy is converted into heat energy, some is overcoming the friction, some is creating sound energy. So lots of another energies are also produced. The required energy, we need a mechanical energy, we need a motion, that is our desirable energy. But along with desirable energy, some undesirable form or degraded energy is also generated. Clear? Next we have conservation of energy. So what is the definition of conservation of energy? According to the principle of conservation of energy, energy can neither be created nor it can be destroyed. It only changes from one form to another form. It means that we can't create energy, we can't destroy energy. We can convert energy from one form to another form. If I'm talking about the mechanical energy, for example, mechanical energy is a sum of kinetic energy plus potential energy. Here M represent mechanical energy, K represent kinetic energy and U represent potential energy. So mechanical energy is a sum of kinetic energy plus potential energy. It means that these kinetic energy and potential energy are interconvertible. Means potential energy is converted into kinetic energy and sometimes kinetic energy converted into potential energy. For example, this ball is now having potential energy. Now it is moving downward, it is changes to kinetic energy. Again it is bounce back and moving upward. This kinetic energy of bouncing back is again changes into potential energy. But the sum of kinetic energy and potential energy remains same, that is a mechanical energy. So this is called conservation of energy. Here as this ball is moving down, potential energy keep on decreasing but kinetic energy keep on increasing. And as this ball is moving upward, now this ball is moving upward, potential energy keep on increasing and kinetic energy keep on decreasing. But one thing is conserved, one thing is constant, that is sum of both kinetic and potential energy, that is a mechanical energy. Clear? So here we will do a theoretical verification of K plus U is constant. Here K is a kinetic energy and U is a potential energy. So sum of kinetic energy and potential energy we will prove it as a constant for a freely fall body. It is a theoretical verification. Why it is a theoretical? Why it is not a practical? Because in the practical air friction is there, but in this derivation we are neglecting the air friction. So for this derivation you can write that we are taking it as a vacuum or friction, air friction we are taking it as 0. So ball at some height is having some potential energy, and when the ball is moving downward, potential energy keep on decreasing, and here initially ball is at rest, so kinetic energy is 0, and this ball kinetic energy keep on increasing. Okay, so potential energy maximum at is moving down. So here what will happen, whole potential energy is converted into kinetic energy. So let's see the derivation. For example, we have a ball which is at some height. Initially this ball is having a potential energy. Now what we will do, we will take three instant. First at the initial position, second at the middle, and third at the ground. So we have took the three instances A, B and C. So these three instant we have, for example this displacement is covered as x, okay, and this whole height from the ground, this is h, and if this is h, this is x, so this is h minus x after subtracting. Now what we will do, we will calculate the mechanical energy at A point, mechanical energy at B point, and mechanical energy at C point. For A, B and C point, mechanical energy is basically, mechanical energy we have sum of potential energy plus kinetic energy. So for A point, for point A, here we have potential energy as mgh. H we have this total H, okay, and at this point initial velocity is 0. If initial velocity is 0, kinetic energy at A point we have half mv square. So here initial velocity is 0, it means that initial velocity we will put it as 0. Okay, this initial velocity we will take it as 0 at A point. So here kinetic energy is 0. So now we have kinetic energy 0 and potential energy as mgh. So now what we will do, we will write it as m is equals to u plus u, here we have mgh, and k kinetic energy we have 0. So total mechanical energy we got it as mgh. Clear? So here total mechanical energy we got it as mgh at point A. Okay, so total energy at A point we have kinetic energy 0, potential energy mgh, so total mechanical energy we have mgh. Now let's see for point B. For point B, or for instant B, here we have, this is x, this is h minus x, and this is total h. Here initial velocity is 0. For example at this point velocity vb velocity we have, velocity at instant B. Clear? So now for the potential energy at point B we have at this point, what is the height from the ground? Height from the ground we have mg, height from the ground we have h minus x. Okay, so potential energy we got at B point is mg h minus x, and we have to calculate the kinetic energy at B, which is half mvb square, half mvb square. So velocity at B point we have to calculate. How we will calculate? By using the third equation of motion, which is v square minus u square is equals to 2as. So final velocity we have vb square, initial velocity we have 0, and 2. Acceleration is acceleration due to gravity because it is a free fall. So acceleration is due to gravity only, g, and total displacement from A to B point we have x. Okay, here it is important thing to note down that total displacement from A to B is x. Okay, so VB square we got it as 2gx. Now put the value of VB square here. So kinetic energy we have half m VB square as 2gx. So 2 and 2 cancel out. So kinetic energy we got it as mgx. Okay. Now we have to calculate the total mechanical energy at B point, which is a sum of potential energy and kinetic energy. Potential energy we have mgh minus x, okay, and kinetic energy we have mgx. Clear? Now we have to open the bracket, which is mgh minus mgx plus mgx. So here we cancel out mgx and we got mgh. Clear? So mechanical energy at B point we got it as mgh. Clear this point? So here at B point we have kinetic energy as mgx, potential energy as mgh minus x, and total mechanical energy we have mgh. So now we have to do the same derivation for a C point. For point C, we have again this x, h minus x, and this is h. Now carefully see, for example, this here initial velocity is 0. Here we have to take, initially the ball is at rest, so we are taking initial velocity as 0 and final velocity we are taking as Vc. Now first of all calculate the potential energy. Potential energy we have mgh. So what is h? This ball is on the ground, means very near to the ground. So here height is 0 from the ground. So height we are taking as 0. So potential energy at this point, at C point, we have 0. Now let's calculate the kinetic energy. Kinetic energy at C point we have half m Vc square. Okay, so velocity at C point we have to calculate again using the third equation of motion. V square minus u square is equals to 2as. For example, from A to C I am calculating. So initially final velocity at C point we have Vc square. Initial velocity at A point is 0. 2. Acceleration due to gravity, again for example A to C, acceleration is due to gravity. And what is the displacement from A to C? Displacement from A to C we have this h. Clear? So Vc square is equals to 2gh. Now put the value here, half m Vc square, so which is 2gh. So from here 2 and 2 cancel out. So kinetic energy we got it as mgh. Now here we have to calculate the mechanical energy, which is sum of kinetic energy and potential energy. Kinetic energy we have mgh and potential energy we have 0. Okay, so potential energy at C point at the ground level, near to ground level, is 0. So mechanical energy at C point again we have mgh. So from this whole derivation what we got, that at each and every point, even though kinetic energies keep on changing, even though potential energy keep on changing, but sum of kinetic and potential energy, which is a mechanical energy, remain constant, which is mgh. Now carefully see, when the ball is moving downward, initially kinetic energy is 0 and at the end kinetic energy is mgh. So kinetic energy keep on increasing when the ball is moving downward, and at the highest point potential energy is maximum and at the lowest point potential energy is minimum. So when the ball is moving downward, potential energy is keep on decreasing, and the whole potential energy, carefully see this point, the whole potential energy, the whole maximum potential energy is converted into whole maximum kinetic energy near to the ground level. Means before touching the ground, the maximum kinetic energy in the body, it is equals to the potential energy initially it is having. So it is also called conservation of energy, in which whole potential energy is converted into kinetic energy. Clear? Next we have to see some note point. First we have initial kinetic energy provided to a body at the ground so as to reach a certain height must be equal to the potential energy of body at that point. For example, if I am taking the reverse of the derivation, if I am giving some force, if I am giving some velocity to the ball, I am giving kinetic energy to the ball and the ball is gaining some height. So according to the conservation of energy, whole kinetic energy must be converted into potential energy. It means that kinetic energy at the ground must be equal to potential energy. So according to the kinetic energy, height must be gained by the ball. So kinetic energy at the initial level I have given as half mv square and potential energy we have mgh. So if I want to calculate up to what height my ball will rise with the velocity, so that value we have v square by 2g. So this is the value of height. Or from here I can also calculate how much velocity I have to give in order to raise the body to a certain height, which is again it is v square is equals to 2gh and v is equals to under root 2gh. For example, they have given you like you have to rise the ball up to 50 meter. So from this formula you can calculate with which velocity you have to give to the ball so that it rise to that level. Clear? Next point we have in the derivation. The derivation we have done, we have ignored the force of friction that I have already told you that we have assumed that friction force is not there. So in the derivation we have ignored the force of friction of the body and the air. So during the free fall, kinetic energy changes into heat also. Means when ball is moving downward, air particles strike with the ball, so some heat is generated, which is actually the loss in the energy. So this loss in energy due to friction, it gets changed and whole potential energy will not converted into kinetic energy because some part of energy is lost in the form of heat. Okay, so the conservative or conservation of mechanical energy is only strictly valid in the absence of external forces. Absence of external forces means absence of this air friction, which is possible in vacuum. Although the total energy is conserved, total energy means what? Like we have mechanical and total energy, we have kinetic energy plus potential energy plus some losses. Okay, heat energy you can also write. So total energy remain conserved, but mechanical energy, which is a sum of kinetic energy and potential energy, is not valid for a real conditions. Why? Because mechanical some losses are there, which is converted their kinetic energy into a part of heat energy. Clear? Next we have, for example, a ball is moving downward and after some time bounce back it is moving upward. Now we have to draw the graph for both the cases. Firstly, we have y-axis, x-axis. So now we have took energy and height. Okay, energy and height above the ground we are taking. Now for example, this ball is moving upward after bouncing back. As the ball is moving upward, which energy is increasing? So here you can write potential energy keep on increasing when the ball is moving upward. This graph I am making when ball is moving upward. Clear? After that I will do when the ball is moving downward. So when ball is moving upward, potential energy keep on increasing, and when it is moving upward its velocity keep on decreasing and here it becomes zero, so kinetic energy keep on decreasing. So this is a graph of kinetic energy, but one energy is constant, that is a total energy or mechanical energy. So mechanical energy, if it is a mechanical energy, if it is a case of vacuum or air friction is not there, so this is a mechanical energy, or you can also write total energy. Total energy remain constant and potential energy when it is moving upward keep on increasing and kinetic energy keep on decreasing. I'm taking the downward case. So in case of downward means when ball is moving downward. Okay, now what will happen? Initially it is having potential energy. So potential energy from this height keep on decreasing. Potential energy keep on decreasing, and in the downward case kinetic energy keep on increasing. So kinetic energy keep on increasing, but mechanical energy or total energy remain same. So this is the graph between energy and height above the ground. Both way we have done, whether it is moving downward or whether it is moving upward. Next we have conservation of energy in simple pendulum. Like in a free fall condition, similar to that in simple pendulum, energy is also conserved. At some point potential energy is minimum and kinetic energy is maximum, and at some point potential energy is maximum and kinetic energy is minimum. So here we have to see at which point potential energy is minimum and at which point kinetic energy is minimum. For example, we have a mean position and two extreme positions. So here we have at this point we have basically a mean position, and these are the extreme positions. So if I'm talking about the extreme position, at extreme position kinetic energy is 0 and potential energy is maximum. Why? Because at extreme position the height from the ground is maximum, or height from the mean position is maximum, but here the velocity of a body is 0. So that's why at this point kinetic energy is 0 and potential energy is maximum. At the another extreme point the story is same. Kinetic energy is 0 because velocity is 0 because it stops at this point, and potential energy is maximum. And at the mean position, we have kinetic energy maximum, which is equals to the potential energy, and potential energy at this point is 0. Why potential energy at this point is 0? Because this is a minimum distance. At this point height is 0. So when height is 0, then potential energy at this point is 0, and whole this potential energy, the extreme position potential energy, whole potential energy is converted into kinetic energy. So that's why at this point kinetic energy is maximum. You can also write kinetic energy as half mv square, but this half mv square is equal to the potential energy when we are ignoring the air friction, which is equals to mgh. So from here again we got the same relation as v is equals to under root 2 gh. So from this relation, if velocity is given, you can find the maximum height, or if height is given, you can calculate the velocity, because 2 and g is constant. So clear? From this part you can do any numerical based on this topic. Clear? With this, our second chapter, that is work, energy and power, is completed. If you have any doubt, you can ask me in the comment box, and for more updates, subscribe our YouTube channel. So thank you to all.